But let's first figure out if this given vector field is conservative, and then if it is conservative, let's find a potential function for the vector field. And we have capital F of xy is equal to 3x squared y squared I plus 2x cubed y j. Alright, so this in front of the I, that's our m. This in front of the j, that's our n. So we need to take the partial derivative of m with respect to y. So the partial of m with respect to y, that's going to be 6x squared y. No, with respect to y, that is 6x squared y. And then we want to do the partial of n with respect to what? X. And so that's going to be 6x squared y. Now, one way that you can remember which way to take the derivative with respect to, for I, we think about I in the x direction, we take the opposite. So we take the partial with respect to y. And then for j, we think about that in the y direction. We take the derivative of what's in front of it with respect to x, kind of the opposite of j, if you want to think about it like that. So what that means is that this vector field is conservative. And so since it's conservative, we can find a potential function for this vector field. The way that we do that is we integrate our m with respect to x, and we integrate our n with respect to y, and then we compare the two, right? So the integral of our m with respect to x is going to be x cubed y squared. Where did the 3 go? When we integrate with respect to x, you divide by 3, so that those cancel out. And then we have plus some function of y. So plus g of y.
So you use the original m?
Yes, you have to use the original. We don't use this that we took the derivative of. We get the potential function from this function here. Alright, and then integrate n with respect to y. So that's going to be x cubed y squared divided by 2, cancels this 2 out, plus some function, and I'll make it h of x. So now we compare the two. If there would have been a function, say, of x in this here, some extra function, then that's what h of x would have been. If there would have been some extra function or some extra term over here in terms of y, that's what g of y would have been. And then we would have just put those with our final answer. But the only term we have is this right here plus a constant. This right here plus a constant. So that means that my function, my potential function, is just equal to x cubed y squared plus some constant. And here, instead of plus c, it's usually plus capital K, which means the same thing. All right. So what about this one here? F of xy equals 15 y cubed I minus 5xy squared j. So let's see if this has a potential function. First, you have to make sure that the vector field is conservative. I'll give you a second to do that. So you take the partial of m with respect to y, and you get 45y squared. You take the partial of n with respect to x, and you get what? Negative 5y squared. They're not equal, so that means that the vector field is not conservative, so we will not have a potential function. Okay? Just write not conservative. Alright, so now we're going to look at something called the curl of a vector field. So the way that the curl is defined the curl of f of x, y, z equals m times I plus n times j plus p times k is equal to, and the notation that you can use, or that is used, you'll just see the word curl and then capital F of x, y, z equals delta crossed with, so that's like a cross product, f of x, y, z. And to make your life easier, instead of having to go through and actually do that, here's the formula that you use. It's the partial derivative of p with respect to y minus the partial derivative of n with respect to z times I minus the partial derivative of p with respect to x minus the partial derivative of m with respect to z times j plus the partial derivative of n with respect to x minus the partial derivative of m with respect to y times k. And I've about run out of room here, so there's my k. So,
Let's say d over dx or dn over dx.
it doesn't say d anything. It says the partial of n with respect to x. That's not a, right here, that's not a 2 if that's what you were asking. Okay, they're all partial symbols. Alright, if the curl of f equals 0, then f is said to be irrotational. the way that you actually get that formula, in case you were wondering, it's just, you know, it's a cross product, and the way that you you have to set up your cross product is like this. So you say the 3 by 3 determinant I, J, K on the first row, partial with respect to X, partial with respect to Y, partial with respect to Z is the second row, and then M, N, and P is the last row. And then evaluate that 3 by 3 determinant and you get the formula that I gave you. So you don't have to go through that every time, just use the formula. It's kind of, you know, like a shortcut. Okay. So let's find the curl F of the vector field. So curl F of X, Y, Z is equal to so let's just I guess I need to tell you what F is equal to. So I'm going to put that up here. Sorry. F of X, Y, Z is equal to 2xyi plus x squared plus z squared j plus 2yzk. So if we just, you can do it the longer way by doing the 3 by 3 determinant, or you can just follow the formula. That's the quickest way. And remember, your M is what's in front of I, your N is what's in front of J, and your capital P is what's in front of K. Alright, so we want the partial of P with respect to Y. That's going to be 2Z minus the partial of N with respect to Z. So that's going to be 2Z times I minus the partial of P with respect to X. That's going to be 0 minus the partial of M with respect to Z. That's going to be 0 times J plus the partial of N with respect to X. That's going to be 2x minus the partial of M with respect to Y. That's 2x times K. So you can see we have 0i minus 0j plus 0k. So since all of this is equal to 0, then capital F is said to be irrotational. So we have we've tested a conservative vector field in the plane to see that it was I guess conservative. So we have tested a vector field in the plane to tell that it's conservative. Well, what about in space in 3 dimensions? It's say that we have some vector field f, capital F of x, y, z equals mi plus nj plus pk. It's conservative if and only if the curl of f is equal to 0. That is, if you think about it, think about this formula up here. So it would mean the partial of p with respect to y has to be what? Equal to the partial of n with respect to z. The partial of p with respect to x has to be equal to the partial of m with respect to z. And the partial of n with respect to x has to be equal to the partial of m with respect to y. Okay, so I can write all those down, but they come straight from that formula. Remember, we want, if it's the whole thing is equal to 0, then all those parts must be equal to 0. We can find the potential function by using the same pattern that we used. We do have to first know that the vector field is conservative, though, to find the potential function. So, for example, let's say that I wanted to find the potential function for, let me write that up here, find the potential function for f of x, y, z equals 2xyi plus x squared plus z squared times j plus 2xzk. Now we've already shown that this vector field was conservative. We found that earlier in the previous example. We found the curl of this function f right here, and it was equal to 0. So we do know that it's conservative. So there's m, there's n, and there's p. So we need to take the integral of m with respect to x, the integral of n with respect to y, and the integral of p with respect to z. All right, so the integral of this with respect to x is going to be x squared y plus, now the constant that we used before, we used g of y, but that's when we only had x and y. So the constant that we have here is going to be g of y x, some function in two variables of y and x.
You keep saying y and x, but you're writing y.
I meant y and z, sorry. Yeah, if I said x, I meant z. Usually we have plus g of y here, but since it's two variables here that we have to deal with, we have a function of y and z. Alright, what's the integral of n with respect to y? X squared y plus z squared y plus some constant, some function of x and z. Alright, and then the integral with respect to p, or I'm sorry, with respect to z, so p with respect to z is going to be just yz squared plus some function k of x and y. Now compare all three parts. You can tell that g of yz is equal to what? This right here. Right? So g of yz is equal to yz squared plus k. What's h of xz equal to? Is there an extra function of xz anywhere in here? Is there a function of xz? No, there's not. So it's just k. And then we have k of xy. Do we have a function of xy in these? Do you see a function of xy? I do. I see 3 of them. Or 2 of them, sorry. X squared y. So it's x squared y plus k. So our potential function, f of x, y, z, is the sum of all of these. It's going to be x squared y plus yz squared plus k. Our capital K is like our C.
Not so we don't have to add them up because it's just some number.
Yeah.
You were just looking, you said G, Y, Z. You just looking for Y and Z.
I'm just looking for a function of yz. That's the only yz out of, well, this one and this one are the same. So out of all 3, we have this term. If these would have been different terms, then it would have been the sum of those 2. But basically what you can do is just take this, this, and this and add them all together. I say you really don't add them together. You just take each type of term, put all those together and put plus k, and that's what I was doing over here. I was just breaking it down to show you what each of these functions had to be.
So if they're the same term, you don't write it twice?
That's right. For the same term, you don't write it twice. That's why we can't just add these together. We have to take the function in terms of yz, the function in terms of xz, the function in terms of xy. Add those together, and that's your potential function.
So if you ain't got a term like your XZ, it's just a K.
Yeah, so if you don't have one, it's just equal to k, constant. Alright, let's do another one of those. See if I can find us one. Let's see. Alright, here's your function. Let's find the potential function if f is conservative. If capital F of x, y, z is equal to xy squared z squared I plus x squared y z squared j plus x squared y squared z k. Alright, so when I took the curl of f, I did get 0, so that is conservative. We'll do the integral of m with respect to x. That's going to be 1/2 x squared y squared z squared. The integral of n with respect to y. Oh, plus, did put my plus g of yz. Partial of n with respect to y. 1/2 x squared y squared z squared plus h of xz, and partial of p with respect to z. So it's going to be 1/2 x squared y squared z squared plus some function I'm going to call lowercase k of xy. You compare the three and you can figure out that g of yz has to be equal to 1/2 x squared y squared z squared plus k, because that's the only function of y and z. H of xz is 1/2 x squared y squared z squared plus k. Similarly, k of xy is equal to 1/2 x squared y squared z squared plus k. So you can see it's the same term over and over and over. So that means that f of x, y, z is equal to 1/2 x squared y squared z squared plus k.
If it's not conservative when you do that, will you still get an answer?
I'm unsure. I think that it won't be useful though.
I mean, you'll get an answer, it'll just be wrong.
Yeah, I think you would get an answer, it'd just be wrong. The last thing for this section, I believe, is called the divergence of a vector field. And the way that you'll see the divergence written is just div of f of xy, or div of f of x, y, z. And so the divergence of f of xy, if f of xy, of course f of xy is just m times I plus n times j. It's going to equal to delta dotted with f of xy, or just the partial derivative of m with respect to x plus the partial derivative of n with respect to y. And then if that's in 3 dimensions, of course, it just picks up one more partial derivative. So it'll be, and of course, then you just have plus pk. You know, so you have f of x, y, z equals mi plus nj plus pk. and that's going to be equal to the partial of m with respect to x plus the partial of n with respect to y plus the partial of p with respect to z. If the divergence of f is equal to 0, then f is said to be divergence free. And all this is right here, this delta, that's like the gradient dotted with the function. So you can actually, if you want to know the divergence at a point for a vector field, you're just going to get a scalar value out, meaning you're just going to get one number out. Okay? So for example, what if I wanted to find the divergence at 2, 1, -1 for the vector field f of x, y, z equals x cubed y squared z times I plus x squared z times j plus x squared y times k. Alright, so we follow our formula. This is a function in 3 variables. Partial of m with respect to x, partial of n with respect to y, partial of p with respect to z. Div f of x, y, z is going to equal partial of m. Remember, this is our m, this is our n, this is our p. So the partial of m with respect to x, that's going to be 3x squared y squared z plus the partial of n with respect to y, that's going to be what? 0 plus the partial of p with respect to z, 0. So all we have is this part of the function here. Our point was 2, 1, -1. So 2 times 1, well no, 3 times 2 squared times 1 squared times -1 is equal to -12. So that is what the divergence at the point 2, 1, -1 is equal to for that vector field. Your book goes on to say that divergence can be viewed as a type of derivative of capital F, in that vector fields representing velocities of moving particles, the divergence measures the rate of particle flow per unit volume at a point. In hydrodynamics, the study of fluid motion, a velocity field that is divergence free is called incompressible. In the study of electricity and magnetism, a vector field that is divergent free is called solenoidal. So this does have applications in the realm of fluid flow and electromagnetic fields. So I'm sure that any of you going into those fields will use this at one time or another. Cut this off. If, one last thing, if capital F of x, y, z is equal to mi plus nj plus pk is a vector field, and m, n, and p have continuous second partial derivatives, then the divergence of the curl of f will be equal to 0. And that's it for this section.